Hello and welcome to our first lesson out of 3 where we will be finding volumes of objects using disks and washers. So in our previous 2 sections, we've been looking at finding areas between curves using rectangles and adding up an infinite number of rectangles, their areas, to find the total area. Today, what we're going to be looking at is the idea of if you have an area that you then rotate around an axis of revolution, this could be an x-axis, y-axis, some external axis, it would create a 3D object. And the question is, how can we find the volume of that 3D object, which is what we will be doing today. So if I have this lovely rectangle, if I want to rotate this around this axis of revolution here, which is considered our x-axis, okay, we would create a 3D object that hopefully we can imagine would look like a cylinder. Okay? So I have this object that has been rotated around which would create a cylinder. Now, the question is, what is the radius of that cylinder and what is the height of that cylinder in order to find the volume of that cylinder, right? The volume of a cylinder is normally pi r squared h, and in this case, our pi is just pi, our r, our radius of our cylinder, would be this distance here. And the question is, well, what is that distance? Well, that distance would be from our x-axis, our axis of revolution, all the way up to the edge of what was originally our rectangle. Well, the height of that rectangle would be f of x. Therefore, our radius of our cylinder is f of x. Now, what is the height of the cylinder? Well, the height of the cylinder would be from A to B. A to B. This here would be our height. Now, if we think about this in terms of our rectangles, we had add all your rectangles up and you get a total area. In the case of a cylinder, we can think of this as a bunch of circles that are being added up from left to right over and over. Here are just some examples until you have an entire cylinder that has been created. So you have all of these little tiny slabs that are being added up on top of each other to create a 3D object. Note that the cross section of the solid is sliced perpendicular to the x-axis. We call this a circular disc. It has a radius of f of x. So the area of one circle would be pi times f of x squared, which would be pi r squared. So again, the important part here for when we get to future lessons is that the cross section of the solid is perpendicular to the x-axis. Let's try a different picture. We will find the volumes in a moment. We're just trying to picture these things and think about all of these circles that we would be adding up together to form our object. And what does this object look like? What shape are we dealing with? Okay. So if I have a triangle, our axis of revolution is still going to be around the x-axis in this case. What shape will we create? Hopefully your answer was a cone. Rotating around this way. So what you end up with is a circular base of your cone. Again, our cross sections are going to be discs or circles. So if I had one in the middle here like this, that's what it would look like. The difference here is that the circles are getting smaller and smaller as you head towards the tip of the cone. Again, we have a radius of each disk, and the radius of each disk is still going to be f of x. It's just that f of x is not the same value as you head from left to right like it was in our previous picture. In our previous picture, as I head from left to right, all of my disks are going to have the same area. In this case, they do not. So in the first one, the cylinder, the disks all have the same radius, which is whatever value, whatever y value this is up here. If it's a 4, these all have radius of 4. The difference here is that the radius is just changing as you head from left to right. You go this way. Okay. So this radius here would be f of a, which is also f of x. It's just a is the value at that point. So again, perpendicular to the x-axis, the radius is f of x. Therefore, the area of each circle is pi times f of x squared. Now, what happens if we are going to rotate around our x-axis, but our shape is not touching the axis? This happens when the area that you are rotating is enclosed between two curves rather than being enclosed with the x-axis itself. Okay, so in this case, our f of x is our top function, which would be this entire height here. This is f of x. G of x is our bottom function, which means that this height here would be our g of x. So when we rotate this around our axis, what's going to end up happening is we're going to have this cylinder with a hole through the middle. You have the hole in this chunk here where you have no function. Okay. So you end up with your inner radius formed by the g of x, which forms a circle when you rotate, and this outer radius, if I drew a better circle, that's probably would have been nicer. And this thing extends down from A to B, and inside you still have that inner tube. So it's essentially a cylinder with a hole through the middle. And in this case, what will happen is you'll have your inner radius being g of x and your outer radius being f of x. So this is your f of x, and this is your g of x. The only reason I'm drawing it like this is so that the two red lines are not overlapping, so it's easier to see the difference here. So if I want to find the area of one of these, each of these looks like this shape here. So you have your inner radius, which is g of x, and you have your outer radius, which is f of x. And so the area of each of these is this blue chunk here, which would be the area of the outer circle minus the area of the inner circle. Area of the outer circle would be pi r squared, where r is f of x, or pi f of x squared. Your inner circle is going to be the area of your white circle in the picture here, which is pi times g of x squared. So your total area is the outer circle minus the inner circle. And again, these are perpendicular to our x-axis. These are called washers. Okay, so the cross section is a circular washer. The other ones were called discs. Okay. These have an outer radius and an inner radius, and our area is pi r squared, where the r is your outer, and minus pi r squared, where that r is your inner. Okay, so in other words, outer minus inner. Sometimes we use big R for outer radius and little r for inner radius. So this is outer and this is inner. So here are some other pictures of circular discs and washers. They do not have to be straight lines. For example, this one is the function y equals square root of x. When we rotate it, it's going to form this lovely looking object here. And we can see that when we have a cross section in the middle, that is still a disc, a filled in circle. This one here is two different functions. When we rotate it, it's going to form this lovely looking guy here. And so hopefully it's a little bit hard to see with the shading, but you can see that we have an outer circle and an inner circle. This shape would be hollow in the middle. And those would be considered washers. Okay. So there are many different visualizations we can have. These are just some samples. Being able to draw these so you can picture what's happening is a very difficult skill that will take some time for some of you. Some people who are very good at visualizing might be okay with that right away, but being able to picture what these things look like will help you write your functions. Okay? So when we think about the volume of each of these objects, essentially what we have is these slabs that are infinitely thin. Okay, so if I scroll back up to the top, we had all of these circles that are adding up together left to right to form one giant object. And similar to how our rectangles had very, very small width, these would have very, very small thickness. So we say that they are infinitely thin. So we have an infinite number of these very thin circles all adding up together left to right to form our object. Okay? So the thickness of each of these circles would be considered our delta x, which in an integral is then our dx. Okay? So if we think about integration as our Riemann sum, we were adding up an infinite number of things. That's all that's happening here. Our integration, we are now adding up an infinite number of slabs with an area A of x. So if S is the solid that lies between x equals A and x equals B, those would be our bounds. The cross-sectional area of that solid is A of x. A must be a continuous function. Then the volume is the integral from A to B of that area with respect to x. Okay? So all this is summing up an infinite number of our slabs. With thickness delta x and area A of x. So remember when we did integration, at the very first part, we were thinking that as area. Now we're basically using integration to find our volume. When we moved on with integration, we thought of integration as antiderivatives. So if you recall, if we did the integral of a velocity function, we got an acceleration function. If we did the integral of a position function, we got velocity. Here we're integrating area and we're getting volume. So that should make some sense that that's what's happening. The derivative of volume is area, so the integral of area is volume. Okay. So that's one way we can think of it. The other way we can think of it is our Riemann sum, the idea that an integral is the sum of an infinite number of things. When we did our Riemann sum, we were doing an infinite number of rectangles, areas of those rectangles left to right. This time what's happening is we are just basically turning those to be perpendicular to our x-axis, and we're stacking them on top of each other. And in this case, they're circles instead of rectangles. Okay. So let's try a few questions. Okay. We're going to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. We're going to start by drawing this. We're going to draw the area that is bounded and then draw what the object might look like. and use that to help us write our integral. These do not need to be perfect. The idea is that it can help you figure out what your radius is going to be. Are you dealing with discs? Are you dealing with washers? And eventually, when you are rotating about axes that are not an x-axis or y-axis, they will help you identify your radius of your multiple functions a little bit easier. Just helps you be able to visualize. Okay. So first we have y equals x cubed. Okay. We have the line x equals 2. This is y equals x cubed. And then we have y equals 0. So our enclosed area is this area in here. It would come all the way down to origin. Okay. We need to know our lower bound. Our lower bound would be here. So when y equals 0, x's would be equal to 0. Okay. So this is going to be our lower bound. This is going to be our upper bound. We're rotating about the x-axis. So what we have is we have this shape here that has been rotated. And so we should end up with, when it gets rotated, we should have a circular base and this bell-shaped object. So it kind of looks like the end of a trombone or a trumpet. And the question is, for each of these slabs that's going to be in here, these are circular slabs. This is what each slab would look like. Okay. These are going to be discs, which means our area is pi r squared. In this case, our radius is x cubed, that's our f of x, right? Our radius will change as I move along this top bell portion, which means our a is pi times x cubed squared, or pi x to the power of 6. Once we have that, we can write our equation for volume, which is the integral from a to b of a of x dx, since we are perpendicular to the x-axis. So this is going to be integral from 0 to 2 of pi times x to the 6th dx. This gives us the same thing as pi from 0 to 2, x to the 6th dx. We can take that pi out, which gives us pi times 1 over 7 x to the 7th from 0 to 2, or pi times 2 to the 7th over 7 minus 0, or 128 pi over 7 is the volume of our object. Okay, so note our cross-sectional area is a disk. Where radius is f of x, perpendicular to the x-axis. And right now, all of yours are perpendicular to the x-axis, but we later will be doing ones that are not. They'll be perpendicular to the y-axis, which means we're going to be integrating with respect to y. So right now, it is important that we remember that this is true because we are perpendicular to the x-axis, meaning the thickness of each slab is delta x. Therefore, we are integrating with respect to x. Let's try another one. Again, I'm going to draw what this thing looks like as an area and what this thing looks like as a 3D object. We have y equals the square root of x. We have x equals 1 and x equals 4. And our second curve is, or our fourth curve, I suppose you could say, but our second curve is y equals 0. So the area that is enclosed by all of these is this area here. and we are again rotating about the x-axis. So that means that our object is starting from here, ending here. It will rotate about the axis like this, which means that I should have circular objects at both ends, and a sample slab would look like this. So again, we have a cross-sectional area that is a disk. Our radius should be f of x. So r is root x. Our area, therefore, is pi r squared, which would be pi times root x squared, or pi x. We have our upper and lower bounds, so we can find our volume. We're going to be going from 1 to 4 of pi x dx, or pi times the integral from 1 to 4 of x dx, which gives us pi times 1/2 x squared, evaluated from 1 to 4. This gives us pi times 16 over 2 minus 1 over 2, or 15 pi over 2. All right, we are going to do a couple more, one more, sorry, not a couple more, just one more. Again, we're going to draw the area, draw the volume, and a sample disk or washer. We have y equals x cubed, and we have y equals x squared. So we have this area in here, and we would need to know our points of intersection because I don't know what my A and my B are unless I know where we are intersecting. Okay? So we're intersecting when x squared equals x cubed, or when x cubed minus x squared equals 0, or when x squared x minus 1 equals 0. So, sorry, x equals 0 or 1. So this is going to be 0 and this is 1. We need to figure out what this thing is going to sort of look like as a 3D object. So we have this sort of slab that looks like this. So when it rotates, it's going to look something like this. And we would have two radiuses, an inner and an outer. Two lines there might make that a little confusing. Let's just leave it at that so you can see what it looks like. So again, it sort of looks like if you turn it sideways, it might look like a flower or like an end of a trombone with a bit of a thicker edge in the middle, something like that. Okay. So the question is, which is our inner radius and which is our outer radius? Well, it looks like our inner radius is this one here, which would be our x cubed function. And our outer radius is this guy right here, which would be our x squared function. So this is a washer, okay, with our inner radius, we'll call this little r, is x cubed, and our outer radius, big R, is equal to x squared. So our area of the washer should be pi times big R squared minus pi times little r squared, which means our area is going to be pi times x to the power of 4th minus pi times x to the power of 6. So therefore, our volume is going to be the integral from 0 to 1 of pi times x to the fourth minus pi times x to the sixth dx, where cross sections are perpendicular to the x-axis, so our thickness is delta x. We are integrating with respect to x. I can take the pi out and have, x to the fourth minus x to the sixth dx, which gives me pi times 1 over 5 x to the fifth minus 1 over 7 x to the seventh, 0 to 1. This gives me pi times 1 over 5 minus 1 over 7, and then you have minus 0, okay, which gives us pi times 7 over 35 minus 5 over 35, and this gives us 2 pi over 35. That's it. There are 3 videos here that might be helpful that illustrate rotating around the axis and what the 2D shape looks like, rotating it to become a 3D shape and how to visualize that. So if you find the visualization difficult, those might be helpful.